So last time we got through the catalytic triad, hydrolyzing the triglyceride to glycerol and a carboxylate, fatty acid carboxylate, three of them. We discussed the fate of glycerol, how it gets modified on one of the OH groups with a kinase to make glycerol phosphate, how that gets oxidized on the secondary carbon by NAD+. To make dihydroxyacetone phosphate, and we showed how that goes through glycolysis. At about the same time, we talked about, we did an overview of what happens to the fatty acid. First, it becomes the coenzyme A thioester, and we will talk through this step. This step consumes a molecule of ATP and releases AMP, which counts basically for two ATPs, because you hydrolyze two phosphoanhydrides as you go through that process. We'll talk about that mechanism specifically a little bit later. Then we gave you an overview of beta oxidation. We talked about how this 14-carbon acetyl-CoA, or acyl-CoA, gets oxidized by FAD to make the trans-enoyl-CoA, which has a double bond between the alpha and the beta carbons. The mechanism of that, which we will talk about today, is just like the succinate to fumarate reaction from the citric acid cycle. Then you install an oxygen at the beta carbon through addition to the electrophilic beta carbon, because alpha beta unsaturated carbonyl compounds are electrophilic at the beta carbon. That gives you this beta hydroxyacyl-CoA, which is just like the fumarate to malate reaction in the citric acid cycle. Then you oxidize the secondary alcohol to the ketone with NAD+. And then lastly, you do what's called a retroclason reaction. And we'll walk through the mechanism of this in a lot of detail. But that essentially clips off a 2-unit acetyl-CoA and leaves, if you start with 14 carbons, 12 carbons. And that goes around and around and around again, back to the start, until you clip off all of the carbons in the fatty acid as acyl-CoA. We talked about how a 14-carbon acyl-CoA is going to undergo beta oxidation 6 times to get 7 acetyl-CoAs. Because the last time through, once you break the bond between the alpha and the beta carbons, you get 2 acetyl-CoAs out. All right? And if we put all that together and matched out everything that happens, from glycerol we get about 18.5 ATPs, and we went through this math, and then from the 3 fatty acids you end up getting 92 ATPs total, and we calculated that from one triglyceride with 14 carbons in each fatty acid you get about between 294 and 295 ATPs. And per gram of fat or oil, that's twice or 2.5 times as much ATP as you would get for the corresponding mass of glucose. We talked about how that's why that's why biology, at least in mammals, stores energy for long term in triglycerides, because you've got half the mass, equal power, equal ATP generating potential. So what we're going to start with today, and I mentioned some of you were worried about all of this math. I mentioned that on problem set 6, which I am still going to write, I will give you an example of what I'd ask you to do as you work your way through this kind of thing. All right, questions about that overview? So let's just dive into the mechanism of what happens to the fatty acid carboxylate. We started in on this but ran out of time last time, and this is the first item on your quiz. We'll walk through it together because it's a little bit unusual. The enzyme that catalyzes this is called a long-chain fatty acyl-CoA synthetase. So this is a funny name. It's one you haven't encountered before. A synthetase is an enzyme that synthesizes something but requires ATP. So a long-chain fatty acyl-CoA synthetase requires ATP to synthesize a long-chain fatty acyl-CoA. All right? So you start out with the carboxylate, and at the end, you're going to get the fatty acyl-CoA thioester. And you've got to use a molecule of ATP to get there. That shouldn't be a surprise because the carboxylate itself is not an electrophile. That's a level 4, not very electron poor. And so what we're actually going to do is break a phosphoanhydride bond in ATP to pay for the thioester bond that we're going to make in this process. So you've seen ATP before, and we've named the 3 phosphate groups in ATP as alpha and beta and gamma. Each of these bonds between phosphate groups is called a phosphoanhydride bond. Each of them is level 1 because you've got an electrophilic phosphoryl group with a low energy phosphorus oxygen pi star, and depending on where you're looking on either side, you've got a decent leaving group. In the case of this particular synthetase, the enzyme actually activates not the gamma phosphoryl group, but the alpha phosphoryl group. So there's the phosphoryl oxygen and the phosphorus and the phosphoryl oxygen. The fatty acyl carboxylate is going to be our nucleophile. The ATP is our electrophile, and the LUMO is the phosphorus oxygen pi star. The leaving group is going to be this pyrophosphate group. It's going to be able to leave because as it leaves, its conjugate acid has a pKa of around 7, so it's a decent leaving group. So what we'll see here is just what you would expect for a nucleophile attacking ATP. The only new thing is we're going to attack the alpha phosphoryl group rather than the gamma phosphoryl group. So attack the phosphorus, electrons kick up, breaking the phosphorus oxygen pi bond, and then you get this pentavalent intermediate that you've seen before in other contexts. Here's the phosphorus. Here's the resulting negatively charged oxygen. There's our carboxylate nucleophile that's now bonded to the phosphorus. And this is the leaving group comprising the beta and gamma phosphate groups. Now, 2 phosphate groups linked together through a phosphoanhydride bond are called pyrophosphate. That's sometimes abbreviated in biochemistry as 2 P's and an I for inorganic phosphate bonded to another inorganic phosphate. It's a leaving group. And so electrons on the negatively charged oxygen can now kick down and kick off the leaving group. And then there is the inorganic pyrophosphate that leaves. Okay. Questions about that so far? Yeah.
So you said the big reason that it attacks the alpha phosphate of the enzyme?
Yeah, likely the enzyme, I don't know, and probably that's just because I'm lazy. I think it probably is known, and you could look it up. 2 ways you could consider activating this phosphoryl group. One would be to have groups here near the oxygen that are hydrogen bonding with just that oxygen. That would stabilize this pentavalent negatively charged intermediate. The other thing you might do is put a magnesium here, a divalent magnesium cation that would tend to neutralize the charge on the pyrophosphate and turn it into an even better leaving group. Okay, others? All right, here is the product of that step. It's called a fatty acyl AMP. And what we've basically done is a nucleophilic acyl substitution reaction or phosphoryl substitution reaction, in which on the phosphorus, on the alpha phosphorus of ATP, we've swapped in the carboxylate and swapped out the pyrophosphate group. But one of the things you should realize now, the effect of that change, kind of remarkable, now has changed the oxygen from the carboxylate into part of a good leaving group. This is the magic of the AMP of this reaction, is it takes a carboxylate, and now the oxygen of that carboxylate, which used to be negatively charged such that the carboxylate was not an electrophile, now the carbonyl carbon is electrophilic, because the AMP group overall is a great leaving group. So that's why that's why the carboxylate is attacking the alpha phosphate, because doing so allows the oxygen, the negatively charged oxygen from the carboxylate, to now be part of a good leaving group. One other thing, pyrophosphate itself still has a phosphoanhydride bond, and so one of the things that helps drive this reaction forward is a pyrophosphate hydrolysis reaction. I don't actually know whether there's an enzyme that catalyzes this or whether it just happens spontaneously, but it's very downhill in energy because it takes a level 1 electrophile and turns it into 2 level 4 compounds. So this is very downhill, and to some extent that pays for the reaction happening. And this is one of the reasons why we say this reaction consumes 2 equivalents of ATP, because you do break 2 phosphoanhydride bonds. All right, once we're to the fatty acyl AMP, and our goal is to get to the thioester, what we need to do is swap out the green leaving group for coenzyme A. All right, so now if you'll forgive me what I'm going to do, since our focus is now going to be on the carbonyl carbon, I'm going to highlight the carbonyl carbon, the carbonyl oxygen. All of this is going to be a good leaving group, because it is once it leaves, it's the conjugate base of an acid whose pKa is around 7. What we want to do now is just what we would expect. Lone pairs on the base are going to deprotonate coenzyme A, then it will attack the carbonyl carbon as a nucleophile and will break the pi bond. That gets us to the tetrahedral intermediate, which we've seen before. Here is what was the nucleophile, and here is the good leaving group. And then, of course, electrons will kick off the good leaving group, and that gets us to the coenzyme A fatty acyl thioester, and releases AMP, which we can take on, react with another molecule of ATP to get 2 molecules of ADP, and then those can be regenerated at the end of the electron transport chain. Okay. So, questions about that? It's basically 2 nucleophilic acyl substitution reactions: addition step, intermediate, elimination step, another addition step, another intermediate, another elimination step. Yeah?
So for pyrophosphate to get to 2 phosphate groups, that's like extremely downhill, irreversible.
Yep. That's irreversible downhill. Basically, water's acting as a nucleophile to attack one of the phosphoryl groups.
So if the phosphates aren't connected to the ATP group,
So if phosphates are not connected to ATP, they exist in this form as ions. Pyrophosphate, as I said, I don't know how long it survives. I don't know what its half-life is and whether there's an enzyme that does this or whether it happens spontaneously. I should look it up. I just don't know. All right, others? All right, well, with that, we are now ready for beta oxidation. So what we're going to do now, based on what you learned from the citric acid cycle, we're sort of going to test what you've learned from the citric acid cycle, because I'm not going to walk you through this. You're going to start with the fatty acyl-CoA. The enzyme that catalyzes this process is called acyl-CoA. That's the named for the substrate and then named for what it does, dehydrogenase. You can tell it's an oxidation reaction because in the product you lose 2 CH bonds and you get a new pi bond. Oxidation of organic molecules is either removal of electrons or removal of CH bonds or increasing in the number of carbon heteroatom bonds. And in this process, the fatty acyl-CoA has been oxidized. In that process, FAD gets reduced to FADH2. Just as a reminder, this hydrogen and its electrons are the hydride that gets delivered to FAD. And this hydrogen here, just the hydrogen, not the electrons, that's the proton that gets delivered to FAD. So see if you can figure out this mechanism. If you need to go back to your notes and look up succinate to fumarate, go for it. The other hint I will give you is the reminder that alpha protons are somewhat acidic. So if you need a clue as to how to get started, removing an alpha proton is a good bet. All right, so take a couple minutes to work on that and let's see what you come up with. I'll give you a minute to get started, then I'll wander around if you get stuck. there's a question that's come up which I think is relevant to everybody, and that's which proton do you remove and which hydride from the acyl-CoA, which proton alpha or beta gets removed and which hydride gets delivered. So what do you think is most reasonable? Okay, alpha, why is that? Okay, so the alpha proton is more acidic. Some people will actually draw an intermediate for this reaction where sorry, I'm just trying to make it smaller so I have space. Some people will draw an intermediate for this reaction where, I mean an R group there, the base from the enzyme deprotonates the alpha proton and electrons go onto the alpha carbon to generate an intermediate that we have called before an enolate. And if you draw the structure of this enolate, one of the things that becomes clear is that it is resonance stabilized because of the adjacent carbonyl group. In contrast, if you were to remove the beta proton and draw that intermediate, the negative charge would just be on an isolated carbon, unstabilized by resonance. So it's actually much easier to remove the alpha proton than the beta proton. So that would mean our mechanism should look like this. Remove the alpha proton. You could just draw an intermediate where the negative charge is on the alpha carbon, or you can skip ahead and have these electrons kick down to form the pi bond. And then hydride gets delivered, and based on the product, where's it going to get delivered to? The lower nitrogen? Yeah, all right. So we go there. Now look, you may need to draw the lone pairs that are implied on that nitrogen so that you can make sure you know what's going to happen next. If we make a new nitrogen-hydrogen bond there, we'd have too many bonds to nitrogen. So we have to move this pi bond here. If we stop there, we'd have too many bonds to the upper nitrogen. So we have to move the pi bond out onto that nitrogen, and we'll also pick up a proton from an acidic group. So this is the orange proton here on that ring, upper ring nitrogen, and this is the hydride that gets delivered to FADH2. The difference between FAD and NAD plus is that NAD plus can accept a hydride with an H with 2 electrons, and that's it. FAD has to accept H minus and a proton so that it can be neutral. You're also going to see later on, and this is kind of weird and just a preview, is that FAD and FADH2 aren't necessarily limited to accepting a hydrogen and 2 electrons at a time. They can actually do some weird 1 electron chemistry, which is hard to draw, really kind of weird, but just as a preview, you're going to see that kind of thing next time when we talk about the electron transport chain. All right, other questions about this? Go ahead.
So this is how I drew it, but would you be able to move the hydride onto the top right nitrogen, and then the resonance pushes it down?
Yeah, there's no reason I can think of why you couldn't move the hydride to the top nitrogen and then push the arrows in the other direction with an acid down here. I don't actually know whether the experiments have worked out which nitrogen accepts the electrons. Presumably, we might look up the crystal structure of this enzyme to see which one is closest to the hydride, and it's probably that one. Okay, good. What else? Okay, so that's our first oxidation step for beta oxidation. The second reaction is not an oxidation reaction. It's simply a hydration reaction where we're going to add water to the molecule. We're going to trade a carbon-carbon pi bond for a new carbon-hydrogen sigma bond on the alpha carbon and a new carbon-oxygen sigma bond on the beta carbon. Okay, so this mechanism, as I said, proceeds by something very similar to the reaction that goes from fumarate to malate in the citric acid cycle. And recall that beta carbons, carbons that are beta to the carbonyl carbon, when there's a double bond between alpha and beta, we call that situation an alpha beta unsaturated because of the double bond carbonyl compound. The beta carbon is electron poor. You can convince yourself of that by drawing a resonance structure for the alpha beta unsaturated carbonyl compound in which you move the pi bond over from alpha and beta to between alpha and carbonyl carbon, and then you break the pi bond and move it out onto the oxygen as a lone pair, and that would leave a positive charge on the beta carbon. So just because of resonance, you can conclude that the beta carbon is somewhat electron poor, and therefore it makes sense that a nucleophile should be able to attack that beta carbon. All right. So let's talk through this together. What do you think my first arrow should be? Yeah, looking at the product, you see an OH group is going to end up on the beta carbon. It used to be water. Where did the proton go? Probably it was removed by a basic group in the enzyme active site. So remove the proton, then what? So the electrons in the bond between the proton that we just removed and the OH group, those should go attack the beta carbon, which we've said is electron poor. Now, there are multiple ways you can show this reaction that are acceptable. And and I'm afraid to, let's see, I need space. I should have given you more space on your quiz for this one. Oh well. Some people show the arrows all in one step. Some people show an intermediate. I will show you how to do both. So from here we deprotonated water, then the electrons from that bond with the OH group attacked the beta carbon. Then we broke the bond between beta and alpha carbons, shifted it over here to form a pi bond, and then broke the carbon-oxygen pi bond and put it out onto the oxygen. That's one option, and that option would give you the following product. The enzyme controls the stereochemistry and water adds from below, and the product of that step is this molecule, which is a resonance stabilized enolate. We could have just as easily drawn this molecule as the alternative resonance structure in which the negative charge is on the alpha carbon rather than on the carbonyl oxygen. Do you guys see how those two options are resonance structures of each other? Because of that, it would have been perfectly acceptable, instead of pushing the arrows like I did, to simply move the pi bond over onto the alpha carbon. So those are two equivalent ways of showing things. They're both acceptable. If two alternative ways of pushing arrows lead to two resonance structures, chances are both sets of arrows are legitimate. Okay. And then, what do you think we do with that intermediate that's called an enolate? Okay, so you anticipate using that acid to protonate the negatively charged alpha carbon. You can do that in one of two ways. You could have, from the resonance structure on the right, lone pairs attack the acid, or alternatively, from the resonance structure on the left, you could do this. Electrons kick down to reestablish the pi bond. The pi bond between alpha carbon and carbonyl carbon breaks. Electrons go onto the alpha carbon, which then gets protonated by the acid. Either of those are okay. Yes?
One function that would be an option, the double bond between beta and alpha just goes straight to the acid and attacks that.
That perfect. No, that's also good. That omits the enolate intermediate, but sometimes we're okay with that because it makes the mechanism a little less time and space consuming to draw. And in some cases, it's difficult to tell whether that's an intermediate or not. And so we'll also be okay with this, in which we attack the beta carbon. That's going to require the bond between alpha and beta carbons to break. At the same time, the electrons go onto the alpha carbon and it gets protonated. This is okay too. It condenses into one step, what I've shown you below. And whether or not that enolate is a intermediate doesn't really matter for our purposes. Okay. Yes?
Question, why during that intermediate wouldn't the lone pairs on the oxygen from the carboxylate attack the acid instead?
Right, why wouldn't we protonate on the oxygen? And the answer to that has to do, I'm just going to abbreviate with an R group, but what you're basically asking, I don't want to do too much. The two different, what you're proposing is whether this situation, I'm sorry, I'm getting it totally wrong. There we go. Whether this situation, protonating on the oxygen, is better than this one, protonating on the alpha carbon. These two that I've drawn for you are actually tautomers. They differ in the location of a pi bond and a proton. This is the keto form because it has a carbon-oxygen pi bond. This is the enol form because it has a carbon-carbon pi bond and an OH sigma bond. In general, keto form is more stable. So it's not that you couldn't, it just doesn't lead you to the most stable product. Okay, others? All right, now you got the oxygen there. It's a secondary alcohol. So this one we'll treat like an actual quiz. I want you to try to draw this now with minimal information. You've done this a few times. Go ahead. Sorry, can you say it again? I missed it.
Like, that's not necessarily carboxylate, it has the coenzyme on it, or is that carboxylate?
You are right. It was never, for some reason, gasp. How offensive is that? How many times did I do that? Be-stinking-leavable. I am ashamed. That's what happens when you don't proofread. That is definitely +1 to everybody that came today. Yep. That is so embarrassing. You are right. The substrate is not the carboxylate. It's the CoA, thioester. Ah. Oh well. Repentance is painful, just like it's painful for me to hand out extra credit points. But it's worth it, always worth it. Actually, repentance is not painful. Repentance is where the pain stops. This is a joyful process, and I'm happy for you getting your extra credit point, all right? Okay. Yeah, so now, go ahead and draw the mechanism. Now that you're detecting errors in me all the time, I am fully confident in your ability to draw the mechanism of this reaction. No hints even, and I'm going to rely on you. If you need a hint, I will draw the structure of NAD plus for you, but otherwise you're on your own on this one. I'll just draw one of the structures of NAD plus. If you like the other one better, you can draw its resonance structure. Okay, off you go. Oxidize that secondary alcohol to a ketone. Okay, everybody ready? Yes. So I'm glad I held on to that. I was going to actually have somebody in front of you and have it.
There's a base involved too, right? But,
Yep.
right.
Yeah, you'll need a base.
Okay, well the base attacks this hydrogen, these electrons make the double bond, and then this will jump down here.
Boom.
I think that's it.
Nice. Very good. Okay, any questions about that? So your standard NAD plus enabled oxidation reaction, just to point out, NAD plus is the oxidizing agent. The beta hydroxy acyl CoA gets oxidized to form the ketone. You can tell that it's oxidized because there's one more carbon heteroatom bond in the product. Of course, NAD plus gets reduced. The reduced form of NAD plus looks like this. And one of those hydrogens on that carbon that's opposite the nitrogen is the hydrogen with its electrons that's going to get transferred to the electron transport chain. Okay, so with that, we are almost done. There's just one more step, but that's a decent breaking point. Let's take a break now, come back in about 5 minutes or so, and we'll finish up beta oxidation.